going to deal with engineering mechanics. We are starting with introduction today, and we'll start with the general principle. You know, mechanics is a branch of physical sciences that deals with the state of bodies at rest or motion that are subjected to forces. And in general terms, mechanics is divided into three branches. Which is one is rigid body mechanics, two is deformable, and three fluid mechanics. But we are solely concerned with rigid body mechanics. And in rigid body mechanics, it is divided into three branches. And we have statics, and we have dynamics. Statics and dynamics. In statics, it deals with bodies that are in equilibrium. And they are either subjected to force or they remain in equilibrium. Whereas this one, dynamics, deals with accelerated motion. Statics, so we have statics and dynamics. And in statics, we say that the bodies will be in a state of equilibrium. Either it is moving with constant velocity or stationary. And we were taught that if a body is moving with constant velocity, its acceleration is zero. Therefore, there is no force on the body. So it has no acceleration, there will be no force. But while dynamics is solely concerned with accelerated motion, where force is applied, the action of the force on the body, and what happens to the body as it moves. And in mechanics, we have some fundamental concepts. And these fundamental concepts are: one, we deal with length. Number two, time. Number three, mass. And number four, force. We have length. And what is length? It simply describes the position of an object, or it gives you the size of an object. It is used in measuring the location or position and then the size of an object. Whereas time is a succession of events. As this event occurs, next to other events. And then mass simply gives the magnitude, the quantity of matter that is contained in that body. And we are told that matter is anything that has weight and occupies space. So the quantity of matter body contains is what is called mass. Whereas force denotes a push or a pull. Whether you push something or you pull it up is what we refer to as a force. And then, before we can continue, there are certain idealizations or theories in engineering mechanics. And what are these idealizations? Idealization is a simple way of explaining a theory. And some of these idealizations we have in mechanics are: one, a particle. Number two, we have rigid body, and number 3, we have concentrated force. Let's look at these concepts of this idealization one by one. The first is a particle. What is a particle? The simple idea that comes to your mind when they talk of a particle is a granule, but that is not a particle, as we consider in mechanics. I could be a particle. You consider me to be a particle depending on the location I find myself. Then, for instance, the Earth is modeled to be a particle because when you consider it and the orbits in which it rotates, a particle has mass, but its size tends to be negligible. For instance, if you consider an aeroplane, the wings of an aeroplane, very large, and then the distance, assuming the aeroplane travels from Calabar to Lagos, and you want to compare the wings of the aeroplane with the distance that it travels from Calabar to Lagos, you see that the wings are considered to be particles, or be very small. Or take, for instance, like this object I'm holding in my hands. If I decide to step out to the school compound, or the whole of this city, and drop it somewhere else, when you look at this, you consider the size of it has mass actually, but the size of it, when you compare it with the city, it's called a particle. So that is a particle. That's particle. And then rigid body. What is a rigid body? A rigid body is made up of many particles that come together but have a fixed shape. They have a fixed shape. The molecular forces of attraction between these many particles are so strong that they do not give the particles the freedom of moving freely at will. When a force is applied to it and removed, the shape remains the same. And so you say it is a rigid body. When a substance, a body that you apply force onto it, before and after, during and after the force, the shape remains the same. Then you consider it to be a rigid body. And then concentrated force. What is concentrated force? We look at this whiteboard I'm using here. If I apply a force of, let me say, 50 newtons onto it, and I use this to push with a force of 50 newtons, the area the force is applying is large. But if I consider the same force of 50 newtons and apply it at this point, we will say the force is concentrated. So the area which I apply the force is very small compared to this. So we say that it's a concentrated force. That is this concept, concentrated force. And then we move to, and in mechanics, it is basically dealing with Newton's laws of motion. And we have 3 of these laws of motion, Newton's laws of motion. We have the first law, we have the second law, and we have the third law. We are going to consider them one by one. In the first law, Newton's first law of motion, it is simply the law of inertia. And what is inertia? Inertia is simply the reluctance of a body to move when it is already at rest, or its reluctance to stop moving when it is already in motion. So the reluctance. So Newton's first law is simply say that every body will continue in its state of rest or of uniform motion in a straight line unless it is affected by unbalanced and unbalanced forces. Or simply, except it is acted upon by external forces. So that is Newton's first law of motion. And then the second law of motion, it simply tells us that if a body is acted upon by a force, the body of a mass is acted upon by a force, that it will give that body an acceleration, and that acceleration is directly proportional to the force that is applied and the more. And then, so you say force is directly proportional to this ma, where m is the mass and this is the acceleration that the force gives. But then, this is just a relation, a variation, but you have to change it to be a law or to form a theory. It becomes force is equal to k ma, where k is the constant of proportionality, and this is the mass of the body, and this is the acceleration this force is given. And we know that the acceleration will move in the direction of the force. And now, we need to find this constant to have a good relationship between the force, mass, and acceleration. And we have chosen that if you apply a force of 1 Newton to a body of mass 1 kilogram, and that it gives it an acceleration of 1 meter per second square. In this case, if we substitute these values here in this equation, we could find out that our k is equal to force all over ma. But now we have a force of 1 Newton, we have a mass of 1 kilogram, and we have an acceleration of 1 meter per second. And so finally we have 1 as the unit here, which is k. Substituting the value of k in this equation above, we have that force is equal to ma. And this is where we obtain the formula for the force, where since k is 1, and then mass is 1, we have force is equal to ma. We move next to the third law, Newton's third law of motion. And what is Newton's third law of motion? It states that action and reaction are equal and opposite. What does that mean? If I have a table, here, and I place an object, let me say this object is laid on top of this table. What happened? That this object, maybe a book or whatever, it is resting on the table with a kind of force downward, and then the table will exert an upward force on this object, equal but opposite to it. And this force the table exerts on the object is called the reaction. It is reacting to the action force that it is. So the action force is equal to the reaction force. That is what the third law is all about. But then, one example is that action and reaction forces are equal and opposite, but they do not cancel each other. Why? The simple reason is that the two forces are acting on two different bodies. Two forces are acting on two different bodies. What does that mean? Let's look at this example to illustrate that action and reaction forces, to show you the difference. If I have an object, let me say a car. I have a car here, and I apply a force of 20 Newton this way, and I apply another force of 20 Newton in the opposite direction. what happens to this car? It remains at rest. It doesn't move. There is no resultant force. And so this remains at rest. It means the two forces have cancelled each other. If they have cancelled each other, then it means that why do they cancel? The simple reason is that the action force and the reaction, they are acting, the two forces in this case are acting on the same body, which is the car. But then, at this point here, there is an action force of 20 Newton on this side of the car. The car also will resist this force that is being applied to it with equal and opposite reaction to this. So similarly here, but since the car does not move, it remains in a state of equilibrium, meaning that these two forces cancel each other. But the action and reaction at this point will do not cancel each other. Then, from here, we have the concept of the weight of the body. The weight of the body. You see, even Newton's law of gravitation, it comes into being at this point. He says, if two bodies lie side by side, if two bodies, they lie side by side, they attract each other with a force, which is given like this. That force is proportional to the two bodies, let's say M1 and M2, that is directly proportional to the product of their masses and inversely proportional to the square of their distance apart. The square of their distance apart. Showing that, which means if two ships are lying side by side in an ocean or in a sea, the other ship will attract the other one to itself. They magnet each other. And the force of magneting one another is proportional to the product of their masses and inversely proportional to the square of their distance. Therefore, we can form an equation from here, just as we did in the case of finding the force. We have F is equal to K, M1, M2, all over D squared. What does this mean? And then from here, we will also need the value of this constant. And in the case of the gravitational attraction, we have a value which is force is equal to G, M1, M2, D squared, where G stands for the constant of gravitational attraction, G. And then let me find out their values. Where we know that where M1 is the mass of the first body and M2 is the mass of the second body, and then D stands for the distance between the two bodies. And from here, in simple mathematics, we see that if we have that force is equal to G, M1, M2 on this square. In some tests, some people use R in this case, R squared, which is the radius or the distance between the two bodies. So I chose to use D, so D squared. And from here, let's say these two bodies have 20 kilograms, and this is 40 kilograms. And then this is a constant, it remains constant. The force existing between them is dependent on the distance between them. Now, you see that if the distance between them is large, being the denominator, by the time you square the distance, it will make whatever is at the top here, the value of F will be very small. But if the two bodies are so close to one another, when you square the distance, even squaring the distance between them, you see that the force here will be larger. It then shows that for two bodies lying side by side, very close, there is the magnetic force between them is very high. Whereas if they are far apart, it's low because of this. And then we have that, let's look at the value of G. We have the gravitational, its value G is equal to 66.73 times 10 to the power minus 12 meters cubed per kilogram second squared. That is the value of G, the gravitational attraction force. And then from this we can we apply it to find the weight of a body. What is the weight of a body? The weight of a particle is simply the gravitational force attracting it to the Earth's surface. And we have that from using this equation of F is equal to G m1 me d squared. What does it mean by this? It means this is still our constant. This is the mass of the body, and this is the mass of the Earth. And this forms the distance between the body and the center of the Earth. And so the weight of a body is given as a force. When you use this Newton's law of gravitation to find the weight of a body, the weight of a body is simply the gravitational attraction of the body to the Earth's surface. And we agree that, remember, D is the distance, m1 is the mass of the body you are wearing, and then me is the mass of the Earth. And then we have that is our weight is equal to G, m1, me, and d2. This square. We have again that W is equal to m times G, where m is the mass of the particle, and then G stands for acceleration due to gravity. The acceleration due to gravity. And we have its approximate value to be 9. G is equal to 9.81 meter per second squared at sea level and latitude 45 degrees standard location, and then which is also approximately 32.17 feet per second squared in different measurements, units, I mean. Now we are going to take a simple example to solve. If we have a body of mass 2 kilograms, if we have a body M is equal to 2 kilograms, each weight will be what? The weight will be W is equal to, it is mg, which is 2 kilograms multiplied by 9.81, which is equal to 19.62 Newton. 19.62 Newton. And then if we have a mass of 3 grams, what does it stand for? What is its weight? First, remember to convert the grams to kilograms, because the unit of measurement for mass is in kilograms and not gram. And so this becomes 0.3 kilogram by dividing the 300 grams by 1,000, because 1,000 grams equals 1 kilogram. So we have 300 grams divided by 1,000, it gives us 0.3 kilograms. And then each weight will be equal to 0.3 kilogram multiplied by acceleration due to gravity, which is 9.81 meter per second square. Now, if we multiply out this, we are going to have 2.94 kilogram meter per second square, which is the Newton. This stands for the Newton, just like here. So the kilogram meter per second square is another unit of the Newton, the force. So we have this as a good example. And then we move next to units of measurement. Let's look at units of measurement. Units of measurement. There are two units of measurement. We have one which is the metric units, or the SI units, System International, the SI units. It deals with we call it MKS, where it deals with mass in kilograms, distance in meters, mass in kilograms, and time measurement in seconds. SI is simply abbreviation for System International or International System. System International or International System of units of measurement. And then it is based on the gram. We have the grams, we have the kilogram, we have the ton, we have the millimeter, we have the meter, we have the Newton, we have the kilonewton, we have the Kelvin for temperature. Kelvin for temperature. Kelvin for temperature. Whereas the second system is the English system, or the British system, or the imperial or US customary system. And what are these? These ones, they are based on the FPS. The force, the pounds, and the second, the Fahrenheit. Sorry, we have the common units of the British system are the pounds. Look at the pounds. LB for pounds. We have the slug. We have the inch. We have the feet. We have mile. We have mile, and we have Fahrenheit. Fahrenheit for temperature measurement. So these are the units of measurement. And then we go to the next topic, which is prefixes. Prefixes. You see, when numerical quantity is either very large or very small, the unit used to define each size may be modified by using a prefix. What does that mean? And some of these common prefixes are given below. Let's see the multiplication. The multiplication factor. We have the multiplication factor, in this some of them. We have the prefix, and then we have the symbol. One is 10 to power 12. 10 to power 12 as the multiplication factor, and then this is tera. You hear of terabytes, you have terabyte. So it's 10 to power 12, and the symbol is capital T. We have 10 to power 9. Yes. 10 to power 12. We have 10 to power 9, which is giga. You hear of gigabytes, it's capital G. And then we have 10 to power 6, which is mega, which is M, megabytes. And then we have 10 to power 3, which is a kilo, and it's K. We have here of kilobyte, and then 10 to power 2. 10 to power 2 is hecto, and we have warhead as a symbol. We have 10, which is deca, and with EA, and then 10 to negative 1, 10 to power minus 1. We have deci. Here, DE are the decimal ones. Then 10 to power minus 2, 10 to power minus 2, which is centi. And it's mostly centimeter. S come up again, and have centi, and then 10 to power minus 3, we have milli, and it's M. Also we have 10 to power minus 6, which is the micro, and the symbol is micro, and then 10 to power minus 9 is the nano, and we use small n, and then 10 to power minus 12 is pico, and we use P. So these are some of the prefixes we have, and we do some simple examples here. Simple example. We have simple example to solve. Suppose we have this value in Newton. What is this value? This is 5 million Newton. 5 million Newton. And then we can say it is equal to 5,000 kilonewton, which is still also 5 mega Newton. So you see the difference? This is 5 million Newton, becomes 5,000 kilonewton by dividing by 1,000, and then dividing further by 1,000, it becomes mega Newton. So the difference, this is by 5 times 10 to power what? 6, isn't it? That's it. And here it is milli. So we have 5 meganewton at last. And then we have another one, let's say 0.003 meters. It is equivalent to what? 3 times 10 to power minus, okay, yes, 3 minus 3 meters. This is equal to 3 millimeters. 3 millimeters. And then we have the next, let's say 5 kilograms. This is equal to 5 times 10 to power 3 grams, which is equal to 5,000 grams. We have sometimes you do this, some people get confused. So there is a conversion rate. How do you convert from one unit to the other? So we look at a few examples. We're dealing with length. Let's take, for instance, length first. If you have a length of 1 meter, the length of 1 meter is equal to 3.28 feet. That is, 1 meter is equal to 3.28 feet. While 1 foot is equal to 30.48 centimeter. And then 1 inch equals 2.54 centimeter, which is equal to 25.4 millimeter. And then 1 mile equals 5280 feet, which is equal to 1609.34 meter, and still equal to 1.60934 kilometer, or approximately 1.61 kilometer. And then, therefore, if we have something like 1 mph, 1 mile per hour, this is equal to 1.61 kilometers an hour. So we have 1 yard. Let's still have more examples. One yard is equal to 3 feet. And then 1 foot is equal to 12 inches. Then for mass and weight, let's look at mass and weight. We have 1 pound. 1 pound is equal to 453.59 grams. And 1 kilogram is 2.205 pounds. And then 1 pound is equal to 4.448 Newton. And then 1 stone is equal to 14 pounds. Further example, 1 stone is 14 pounds. one slug is equal to 32.17 pounds, which is equal to 14.59 kilograms. And then 1 pound is equal to 16 ounces. 1 kilogram is equal to 9.81 Newton. Then for the temperature, look at temperature conversion between Fahrenheit and degrees centigrade or Celsius. We have degrees Fahrenheit is given as 9 all over 5 degrees Celsius plus 32. That is converting the degrees Fahrenheit. We want to convert it from the degrees Celsius is 9 over 5 degrees Celsius plus 32. This has been done in secondary school. And then the conversion for degrees Celsius is equal to 5 over 9. You see the fraction here as reversed into F, that degrees Fahrenheit minus 32. That is in degree Celsius. While the Kelvin, the absolute is equal to the degree Celsius plus 273.15. Change it to Kelvin. That is, you add the degree centigrade, you add 273.15 to degree centigrade, you have the temperature scale to the Kelvin. And then for volume, when you consider volume, consider conversion to volume. We have that 1 liter is equal to 1,000 cm3, which is the same thing as 1 meter cube. 1 meter cube is 1 meter cube is 1,000 liters. We have examples now in the example for unit conversion. The question is convert 3 kilonewton to kilogram. 3 kilonewton to kilogram. We know that the solution is 1 kilogram is equal to 9.81 Newton, which is equal to 1 Newton. 1 Newton equals 1 all over 9.81 kilograms. And then 1 kilonewton is equal to 10 to the power 3 Newton. And this implies that 3 kilonewton is equal to 3 times 10 to the power 3 Newton, which is equal to 3 times 10 to the power 3 on 9.81 kilogram, which is 305.81 kilogram. And then the second example. Our second example is to convert 20 pounds. Convert 20 pounds to kilogram. 1 pound equals 453.59 grams, which is equal to 0.4539 kilograms. This implies that 20 pounds is equal to 20 times 0.4539 kilogram, which is equal to 9.072 kilogram. And then the third example, let's look at the third example, is to convert 670 pounds the feet cube to kilogram per meters cube. We have that 1 pound is equal to 0.45359 kilograms, and 1 foot is equal to 30.48 centimeters, which is equal to 0.3048 meters. Implying that our 670 pounds feet cube is equal to 670 times 0.45359 kilogram on 0.3048 meter power 3. This gives us the final solution to be 1073.314 kilogram per meters cube. And then our penultimate example, last but one. Before we close for the lecture today, convert 5,000 inch squared to meter squared. We have that 1 inch. 1 inch is equal to 2.54 centimeters, which is equal to 2.54 meters over 100. Over 100, which is equal to 0.0254 meters. Now, we have our 5,000 inch squared equal 5,000 into 0.0254 meter squared, which is equal to 3.2258 meters squared. That's great. I think we can stop here for today. We'll call off next lecture will be on force vectors. So you can subscribe to this YouTube for more exercises, so that when next time I place a video there, you can easily get alert. Thank you.
Good afternoon.